So first of all, I'd like you to welcome Professor Charles Burnett from the University of London, who's going to be talking about Al-Birūnī and Ibn al-Haytham, two outstanding polymaths of 11th century Islam. Charles.
Well, I certainly appreciate the briefness of the introduction. I shall be talking, as you can see, about two polymaths, so you get two for the price of one. And it depends, actually, how the time goes as to whether I have much time to talk about the second one. So I'm going to be concentrating first on Al-Birūnī, or simply Birūnī, and then, if there's time, we'll be talking about Ibn al-Haytham as well. Polymaths do not arise in a vacuum. They're not like the philosophers autodidactus of Ibn Tufayl, who learns everything from his observations on a desert island. They arise within a tradition of scholarship. It is not coincidental that three polymaths arose at the same time. Two of them came from what we might consider, at first sight, a remote part of Central Asia, namely Ibn Sina from Bukhara. See if this works. Ibn Sina from from Bukhara here, who lived from 980 to 1037, and Birūnī from Kath on the same Amu Darya river, just a little bit further up, which was the capital of Khwarazm, who lived from 973 to 1048, almost exactly contemporary. And both are living in a Persian language region, but close to the Chinese border, in this direction, of course, and also not too far from India, which, of course, is just round here. And the third polymath is Ibn al-Haytham, again contemporary, 965 to 1040, who came from Iraq, the central region of the Arabic realm, and his native language was, of course, Arabic. So he came from Basra, which is in the corner here, wherever here we go, there's Basra. Abu al-Rayhan Muhammad ibn Ahmad al-Birūnī's life story can be briefly told. He spent the first part of his life in Kats and Gorganj, the successive capitals of the Ma'munid Khwarazm Shahs, the kings of Khwarazm, until 1017, whilst also visiting Rai, that's somewhere near, around about here, near present-day Tehran. Anyway, near present-day Tehran. And while Khwarazmian, a dialect of Persian, was his native language, he would have been brought up with a knowledge of Neo-Persian, which was especially suited for literature. The Shahnameh and all these great Persian epics were composed at this period, and Arabic, the language used for writing scientific and philosophical works. Among the scholars of the thriving court of the Ma'munids were Avicenna, Ibn Sina, with whom Birūnī corresponded in his youth. And Avicenna was even younger than him. He was a teenager, Birūnī was 22 at the time. And also Abu Nasr al-Mansur, who taught Birūnī and worked with him on astronomy and mathematics. Birūnī was following in the steps of the greatest Khwarazmian mathematician of the previous century, Muhammad ibn Musa al-Khwarizmi, from which we get Indian numerals, algebra, and indeed the word algorithm, and also of the prolific scholar and translator from Greek, Costa ibn Luca, a Christian, who is said to have spent his last years in the service of the Khwarazm Shah. As well as having access to the Greek classics in the sciences and philosophy, translated into Arabic, he apparently learnt the Greek language itself in this environment. The last members of the Ma'munid dynasty, Ali ibn al-Ma'mun and his successor and brother Abu Abbas Ma'mun, both married sisters of Mahmud, the ruler of Ghazni, the Ghazni emperor. And you can see Ghazni is just south of Kabul here. There's Ghazni. And in 1017, Mahmud himself invaded and conquered Khwarazm and took many of its leading figures to Ghazni as prisoners. Among these was Ibn al-Haytham, who complained about his treatment, Al-Birūnī, who complained about his treatment, but was eventually able to study, observe, and experiment, and accompany Mahmud on his journeys to northwest India, which came under his control, so over here. So there, Birūnī added to his quiver of languages Sanskrit. And by the end of his life, he had composed at least 146 works in Arabic and sometimes Persian. Most of his work is concerned with the cataloguing of information. The early work, known as the chronology, al-Athar al-Baqiya min al-Qurun al-Khaliya, meaning the remaining signs of past centuries, gives the eras of the creation, the flood, and 13 other eras, month names used by 12 different races, regnal tables, 11 of them, pseudo-prophets, Sabaeans, followers of Bodhisattvas, Zoroastrians, Manichaeans, etc., and festivals of 11 different peoples. It is interesting that remains, in the title, Al-Athar, are classified by different time scales. Memories are embedded in days, months, and years. So we have here an example of applied mathematics. In his Tahdid, or in full, the determination of the coordination of places for the correction of distances between cities, he gives interminable lists of the coordinates in latitude and longitude of different locations. In his Tafhim, the instructions on the foundations of the art of the stars, he gives a full account of every astrological doctrine and term. He wrote this in Arabic, but also in Persian, the latter being addressed to a woman of the court. Whether he believed in the material that he is describing is not so relevant. For example, in astrology, which he criticized heavily in another context, and yet he consulted astrologers to find out how long he had to live when he suffered from a severe illness. But anyway, what he was concerned about was that any science or pseudoscience had its own range of terminology. What he does do in the Tafhim is to show how astrology is located within mathematics, astronomy, and cosmology, and how instruments, and the astrolabe, the quadrant, etc., serve astrology. And here's a picture of the astrolabe. You can see what's called the rete up here. Well, I've got it here. Yes, the rete. And you can see, the lines of azimuth and so on, which give both the picture of what the heavens look like and its relation to the local climb, and another picture up there. And these all are very detailed, actually, descriptions of the astrolabe. He calls his longest book, the one which we call On India, Tahqiq mal lil Hind min Mukala Makbula fi al-Aql aw Ma'dula. So verifying all that the Indians recount, the reasonable and the unreasonable. Here he describes and itemizes the whole culture from direct experience when he was visiting India with Mahmud, and from the writings in Sanskrit. He says that Sanskrit is a terrible language to learn, but he mastered it and he translated from it. And so we have the caste system, we have literature, Indian literature, we have places and distances between places, time intervals, rites, pilgrimages, diet, etc. A very, very wide range of subjects. In the Qanun al-Mas'udi, addressed to the successor of Mahmud of Ghazni, we have the most comprehensive of Birūnī's astronomical works. And it consists of page after page of tables giving the positions of the planets, the sun and the moon at any time and place, and a description of the places of 1,029 fixed stars. And this is just one example. These are describing the fixed stars, giving values both in Indian numerals. Well, this is the printed edition, so I'm not sure quite how it coincides with the manuscripts, but also in Arabic alphanumerical numerals, and the place in the constellations, etc., of the fixed stars. His book on gems brings together material from Hellenistic, Roman, Syriac, Indian, and Islamic sources, whilst his pharmacy is an alphabetical listing of 720 drugs, medicines, and for each entry the name is given in Arabic, Syriac, Greek, Persian, and an Indian language, and sometimes some local languages from Central Asia. His cataloguing of the works of the doctor and philosopher Abu Bakr Zakaria al-Razi, who lived from 865 to 935, the best known scholar, doctor, philosopher from Rai, where, of course, Birūnī visited. And he catalogued the works, and he added a list of his own works to this catalogue. This is the longest list we have, but we know that he composed some works after this date as well. And this is also an indication of his love for listing comprehensively. So, should we call these works encyclopedias? Well, not exactly, because Birūnī backs up or introduces his data with theory. In the chronology, he discusses the astronomical paradigms involved in calendars, the determination of the length of human life, stereographic projection, how to depict a three-dimensional sphere on a plane, etc. In his Tahdid, he gives the mathematical formulae for determining latitudes and longitudes. In the Qanun al-Mas'udi, he discusses cosmological principles, that the earth and heavens are spherical, the earth is stationary, the principles of trigonometry, astrological operations, etc. And I think we've got one, well, here's one picture just of the phases of the moon. You can see there's the earth on this side, and then the moon is going round. And you can see this successive dark areas of darkness and lightness of the moon as it circles the sun. Well, as it circles the earth, actually, and reflects the light of the sun. So we've got all these sort of works into which mathematics or numerals are introduced or analysed by mathematics and numbers. But other works dealt with particular instruments or particular mathematical problems. The astrolabe, the quadrant, or the determination of the density of an object. Others could be described as a meditation on a single word. For example, he wrote a book on shadows, or the longer title is The Specialized Treatise on Shadows. And this not only deals with philosophical notions about the nature of light, shade, and reflection, and mathematical calculations of the obliquity of shadows, but also quotes poets' evocation of shadows in metaphors and evoking a particular season of the year or location, as well as the concept of shadow itself in Sanskrit and Middle Persian. Gerald Toomer, the great historian of Arabic mathematics, has characterized his work as, I quote, following through a chain of thought, one might even say free association, as a result of his boundless curiosity and enormous stock of information, which, Toomer says, leads him from one digression to another. For example, a discussion of the measuring time by man's shadow leads him to the influence of the shape of the human head on the length of the shadow, thence to the custom of the Khwarezmians of artificially flattening the heads of their children, next to a passage from Hippocrates on similar practices in antiquity, and finally to Galen's criticism of Hippocrates on this. This is a typical way of going from one subject to another, just keeping the word, shadow in this case, as the common denominator. The names of gems, too, clearly fascinated Birūnī. He traces their etymology and quotes their appearance, again, in poetry. He composed, as he does in his pharmacy, and he composed poetry himself. We have some evidence of this. His wider interests are manifest in his India, where he includes the discussions of the nature of God, of the soul, of matter, mysticism, paradise and hell, always seeking within Indian culture the universal, what he believed to be universal beliefs that were presented most clearly in Islam. He translated a Sanskrit Buddhist text on theology and philosophy, Patanjali's Yoga Sutra, which dealt with the liberation of the soul and its detachment from the external world, the attributes of God, the power of spirit over the body, and the composition of the universe. So one can say that we find two leitmotifs in Al-Birūnī's writings. The first could be said to be numbers. Birūnī showed great interest in astronomy and related subjects, and one could say that he favoured subjects to which mathematics, counting, dividing, calculating, listing, etc. could be applied. Perhaps he was obsessed with numbers. For example, hidden amongst the facts in the chronology is a comprehensive enumeration of chessboard moves. He was obsessed with accuracy, particularly numerical accuracy. The second leitmotif is language. Most philosophers and scientists work especially with one language. Birūnī worked with several, writing texts in Persian and Arabic and making translations from Sanskrit. But he was also fascinated with etymologies, constantly comparing terms in different languages and delighting in poetry. I would like to end this account of Birūnī, with his own, what he says about his aims and attitude. First of all, he is not afraid of expressing his awareness of his own lack of knowledge. In the chronology, he freely admits not knowing the Indian method of calculation, of intercalation, where you have extra days to make up for the difference between the lunar year and the solar year. He says, I have not met with anybody who had an accurate knowledge of this subject. Therefore, I turn away from what I cannot know for certain. Secondly, his acceptance of the possibility of other ways of explaining phenomena. In chapter 26 of his India, for example, after mentioning Brahmagupta's and Varahimihira's criticism of Aryabhata's theory of the rotation of the earth, I mean, these are all Indian scholars writing in Sanskrit that he reads directly in the Sanskrit, he says, the rotation of the earth does in no way impair the value of astronomy, as all appearances of an astronomical character can quite as well be explained according to this theory, the earth circulating, as to the other, the stationary earth. And he says it is the same whether you take it that the earth is in motion or that the sky is in motion, for in both cases it does not affect the astronomical sense. It is for the physicist to see if it is possible to refute one or the other theory. And thirdly, related to this, is his refusal to concentrate on refuting his opponents, which was an age-old custom. I mean, going back to Aristotle, who spends a lot of time refuting his other theories. And again, in his book, India, he says, this book is not a polemical one. I shall not produce the arguments of our antagonists in order to refute such of them as I believe to be in the wrong. My book is nothing but a simple historic record of facts. I shall place before the reader the theories of the Hindus exactly as they are, and I shall mention in connection with them similar theories of the Greeks in order to show the relationship existing between them, the Greeks and the Indians. There is no doubt that Birūnī was a polymath. He was learned in many different fields. He must have had a phenomenal memory and a gift for mathematics and languages. Many people have seen in him a pioneer of anthropology and comparative religion. His influence in the Islamic realm and even in neighbouring areas was immense. I need only refer to the fact that a peculiar irregularity in Mercury's first equation table, it's an astronomical theory, which he introduces in his Qanun, is attested also in the Chinese text entitled Hui Hui Li, which means the Islamic calendar, composed in Beijing in 1383. It is not surprising, perhaps, that in 1962 his native city of Kath was renamed Birūnī, a name it retains to the present day. Do I still have 5 minutes? No. Keep going, okay. 10. What may be surprising is that his works, even his name, were not known in the Christian West. I mean, there's a French text which refers to Al-Birūnī, which could be him, but it's very difficult to be sure. None of his works was translated into Latin, even anonymously. This contrasts greatly with the second polymath that I'm going to mention more briefly, Abu Ali al-Hasan ibn al-Haytham, who lived from circa 965 to 1040. While Ibn Sina and Birūnī both came from Transoxania beyond the river Amudarya, i.e. the Oxus, Ibn al-Haytham, though contemporary, came from another part, a completely other part of the Islamic realm, namely southern Mesopotamia. He is also distinct from Birūnī in that he was well known in the Christian West. This second Ptolemy, Batlamyus Thani, named after the great Greek astronomer, was born in Basra, but invited by the Fatimid Caliph al-Hakim, who ruled from 996 to 1021, to Cairo, which had become, as it were, a second Baghdad. Or even the replacement of Baghdad with the Fatimids, in that al-Hakim had built an observatory and a library which he called Dar al-Ilm, the House of Knowledge, which rivaled or replaced the Bayt al-Hikmah, the House of Wisdom in Baghdad. Ibn al-Haytham survived into the reigns of al-Zakhir, Izz-ad-Din Allah, and al-Mustansir Billah, to 1094, who reigned till 1094. Well, of course, Ibn al-Haytham had died by then. Like Birūnī, he made a list of his own works, which included 25 works on mathematical sciences and 44 works on Aristotelian physics and metaphysics. He is credited with developing the scientific method in that he used experiments to test a hypothesis, rather than experiments in the sense of just observing or discovering. The best-known quotes of his method are that, I quote, "I constantly sought knowledge and truth, and it became my belief that for gaining access to the effulgence and closeness to God, the great light coming from God, there is no better way than that of searching for truth and knowledge. And the collateral of this is, if learning the truth is a scientist's goal, then he must make himself the enemy of everything that he reads. He must be severely critical." This ultra-skeptical attitude contrasts to what we've heard about Birūnī's viewpoint, which is much more tolerant of those who held contrasting views. It has been noted that while Birūnī's works are full of colour, fascinating anecdotes, things poised on the boundary between truth and fiction, Ibn al-Haytham's works are dry and methodical. Roshdi Rashid has published 5 thick volumes of his mathematical works, but his most famous work by far is his Kitab al-Manazir, or Optics, which, in the course of its 7 books, combines the anatomy of the eye with detailed geometrical analysis of direct vision, reflected light, distorted visions, refraction of light, and much else. It establishes the principle of the intromission theory of vision, whereby the eye receives rays directly from the object of sight rather than sending out a spirit to retrieve the image and bring it back to the eye. In the East, it was revised by Kamal ad-Din al-Farisi, who lived from 1267 to 1319, in what he called the Tanqi al-Manazir, the revision of the Optics. In the West, it was translated into Latin in the late 12th and early 13th centuries, apparently by 2 scholars, one more literal and the other more elegant, writing more elegant Latin. The middle name of Ibn al-Haytham, al-Hasan, was adopted as the scholar's name in the Latin context, becoming al-Hasan or al-Hasan, perhaps because people were aware that al-Hasan meant the good man. We see this quoted. As such, he became a household name in the West and the subject of glosses and commentaries. His optics were influential on the optical writings of Roger Bacon, John Peckham, Erasmus Vitello, who, this last one, in turn wrote a revision of the work. In 1572, Friedrich Risner published the medieval Latin translation for the first time. This enabled Johannes Kepler and René Descartes to use it extensively in their own works on optics. We might learn more about this later on. But one thing that he is famous for is a problem that he was the first to set out and which was named after him, Al-Hasan's problem. Well, I won't go into detail as what Al-Hasan's problem is. I mean, this is just one diagram reconstituted from his optics, from the Arabic manuscripts, and you can see how complex it is. But here is Al-Hasan's problem as set out in Al-Birūnī, who has the advantage of, often quoting Ibn al-Haytham literally, but adding the necessary diagrams. So this diagram is from Al-Birūnī, there it is in closeness. And I can say, I mean, those who know the mathematics well may recognize this. Given a light source and a spherical mirror, find the point on the mirror where the light will be reflected to the eye of an observer. I can't go into details as how that relates to that diagram, but all I can tell you is that it wasn't until Christian Huygens, who lived in the 17th century, eventually found an elegant way of solving this problem. I would like to end this presentation with a couple of images from Risner's 1572 edition of the medieval translation of Ibn al-Haytham's Optics, called in Latin the Opticae Thesaurus. And here we have the title page. You can see the top, Opticae Thesaurus, al-Hazani, so al-Hazan is the Latin name, Arabis, he's an Arabic man. There are 7 books, and this is edited or printed published for the first time, and then there's a little work by him also, and then Vitello's revision of the whole work, and I think it's illustrated with many figures and increased with many figures, and then we have Frederick Risner's name and the place and date of publication, Basel in 1572. What is most famous, maybe, is the frontispiece, which encapsulates very nicely the whole of the subject matter of Ibn al-Haytham's Optics. Here we have the 3 kinds of vision, which is direct, reflected and refracted, about which optics debates and the arguments of the 3 kinds of vision. And you see here, there's some refraction down there, naked man standing in water. And here you have reflection, probably even Al-Hazan's theorem. I mean, where does this man see the image of this object? We have burning mirrors. You've got the mirrors reflecting the light of the sun and burning up this ship. And I think, I mean, if you spend some time on this, you can recognize other aspects. I mean, you've got the rainbow. You've got some, I don't know what the sunken ship is doing. Well, that's probably already been burnt and it's sunken in the river there. So you can contemplate that a while. In your own time, because I also thought it would be interesting. Oh, why is that funny? That is at the very, it's the 3rd book of the Optics. I could have shown you an Arabic picture of the physiology of the eye, and you can see the various tunics, the various, the optic nerve coming from the brain to the eye, and the detailed description of what happens from a physical point of view when the eye perceives an object. And finally, I have this image of Ibn al-Haytham. You see him at the side here, dressed as an Arab. He's got in his right hand some geometrical diagram, and underneath he's described as being al-Hasan, and he does things by ratio. He uses reason. And I think this picture is a picture of a brain. I mean, it's very difficult to depict a brain, but the brain stands for reason. And this, he's holding up a banner, as it were, which is advertising Johannes Hevelius's Selenographia, published in 1647, which was, in fact, the first book to attempt to map the surface of the moon. And the person who's holding up the other side of this banner is none other than Galileo. And Galileo is said to use the census, and the image accompanying Galileo is an eye instead of the brain. So you can see that he's parallel, as it were, on the same level as Galileo, and this reflects his importance, at least in the West. I mean, I could go discuss a little bit further his relevance in the East, but certainly he is a polymath as far as Western scholars and readers were concerned. So you have two polymaths for the price of one. We could have added Avicenna, whose legacy was as great in the West as in the East. I mean, he combines both. Al-Birūnī's influence is in the East, and Ibn al-Haytham's mainly in the West. Avicenna is a great man in both traditions, but it would have taken up too much time to discuss this third contemporary polymath. Thank you very much.
Well, thank you. I think you'll all agree that that was a wonderful talk in the middle.
You didn't say much about sort of biological knowledge or animals or plants, that kind of thing. So was that somehow regarded as a different domain? Because you'd think that's something that you see all around you, so you would be interested.
Well, I mean, Birūnī was describing hundreds of plants and so on of India, and in his pharmacology, I mean, when I say drugs, I mean plants that are used in medicine. Well, not just plants, but also minerals, muds and other things. I think we saw briefly that Birūnī separates the methods of mathematics from the methods of physics. And physics could be coming to different conclusions from mathematics, as it were. I mean, he believed that astronomy explained the phenomena very well. But he didn't go on to say, well, this coincides exactly with the shape of the universe, which is established by physics. And so within physics or natural science, he would include both well, cosmology above the sphere of the moon, but also everything below the sphere of the moon. He wrote about comets, he wrote about things in the atmosphere, and of course things on the surface of the earth, which are plants and animals and minerals, the three realms of nature. No, maybe that's another lecture to investigate exactly how he approached physics. But for him, I mean, in a way, he was very like Aristotle, who also was a great classifier in his De Animalibus and his various books on animals. He just went on from one animal to another, describing its characteristics.
Right, we've got another question in the middle of the row near the back, the person with the red jacket on. Oh, okay. Yes.
Thank you very much, Charles. One thing which, well, many things have always fascinated me, but one which has fascinated me in particular is the lack of translation of Al-Birūnī or knowledge of his works in the West. He's so accessible, as we would nowadays say, yes. So readable. Do you have any idea why?
Yes. Well, possibly because he was right out in the east, in Ghazni and Khwarazm, and whereas Ibn al-Haytham was more central in the Fatimid empire of Cairo. I mean, he's so popular these days. I mean, the Russians think of him as their great hero, as it were, and that's why they named Kat and Birūnī. But what I'm not so sure about is just what his immediate influence was, even in the Arabic Islamic world. We know of Persian translations, but they were his own. I mean, he wrote the Persians. It's not as if other people were translating his work into Persian or Urdu or whatever. So I'm afraid I can't say exactly how popular, how many manuscripts of India or the chronology there are. But even so, it is striking that he's unknown in the West.
There's a question here, right in the middle of the front row.
So my question is about mirrors. You mentioned the spherical mirror, which Huygens solved.
Yes.
Did your optician consider the parabolic mirror, either mathematically or practically?
Oh, he got a whole book on mirrors. I mean, I'm sure, yes, because I mean, the first 3 books of the optics of Ibn al-Haytham are on direct vision, but the next 4 and 5 are on reflection. So he's considering all kinds of mirrors. And of course the camera obscura. I mean, he's...
And would he have been involved with practical construction of such things, or is it just a theoretician's point of view?
Oh, that's a good question. Yes, yes. One associates Birūnī more really with the construction of all kinds of astronomical instruments and probably even
because you showed an illustration of burning a sail. It's all very well to imagine it, but were they actually building such things and using them as weapons of war?
Oh, I'm sure they. Excuse me. I'm sure they were. Yes, yes. But well, correct me if I'm wrong, but I can't immediately think. I mean, we think of Ibn al-Haytham really as primarily a theoretical mathematician or an astronomer, rather than someone who, I don't think he wrote, did he write a book on the astrolabe? I don't think he did. And he, I mean, that again might be one reason why his works were diffused, because they were written. But I don't recall that there's much evidence of him. I mean, he must have done some practice, but we don't associate particular instruments with Ibn al-Haytham.
There's someone here, and the 3rd row back, second from the end.
Thank you. I'm interested in Ibn Haytham's touch on scientific methods you mentioned.
Oh, yeah.
Being enemy of everything he knows.
Yes, yes.
Was that a qualitative approach coming out of him, or did he actually use elementary scientific methods in his thinking? And if he did, why was it not taken by his taken up by his contemporaries and future generations?
Yes, well, there's a whole tradition in Arabic scientific writings of shukuk, of doubts about, and Ibn al-Haytham also wrote doubts about Ptolemy. So he's not unique in not taking things for granted that even his very eminent predecessors discovered or stated. Sorry, I should, to go back to the previous question, of course in the optics there are lots of constructions. And whether they're put into practice, I don't know, but one construction is indeed that of the camera obscura, where he actually discusses in quite detail how to build the room with a little hole in the wall, by which you discover that the image is reversed when it goes through the little hole. But I think Ibn al-Haytham was supposed to be even more concerned about, starting from scratch with every investigation and not relying on his predecessors.
Yes, there's a person in the orange jacket.
Yeah, Charles, just to pick up on this this point about the burning of the ships, my understanding is it's the legend of Archimedes.
Oh, yes, yes.
And
yes.
Leonardo had a go at it for his patron in Rome, who was Giuliano de' Medici. But whether anybody took it seriously or not, this is kind of typical frontispiece rhetoric.
Yes, I don't know, because, you have whole texts in Arabic and translations in Latin on how to use a burning mirror, and the Mirara Ikhtirak, whatever it's called, Mukhtarak.
Go at Al-Haytham's problem using what we would think of as a pantograph,
yes.
a series of wooden levers and so on. So he
did it
instrumentally, as it were.
Well, it's I can't say, but it's a very picturesque legend, as it were. when you see the ships burning up.
There's a question here.
Thank you. How does their scholarship and scientific knowledge compare with what was happening in the West at the same time?
It was miles ahead. I mean, we're talking about the early 11th century and what was happening in Europe in the early 11th century. I mean, and any scholarship, any scientific scholarship that was already happening in that case was derived from Arabic, again, Arabic texts on astronomy, on the astrolabe, on astrology, which were translated in the late 10th century in Catalonia. That's the beginning of the transmission of Arabic knowledge to the West. And I mean, we do have a lot of experimental science, as it were, with Bede, who's actually looking at tides and looking at the waxing and waning of the moon. But theoretical science or theoretical mathematics is almost non-existent. A bit in the computers literature, I suppose, in calculating the dates of Easter and the other movable feasts. But integrated scientific, mathematical, geometrical, astronomical science only comes in from translations from the Arabic, very many of which are in turn rely on translations from Greek into Arabic, like Euclid's Elements, Ptolemy's Almagest, and so on. But they only come in large numbers, or in significant numbers, in the 12th century. So in the middle of the 11th century, these whether you're talking about Al-Birūnī or Al-Mansur or Al-Masih or Masihi, another doctor, they were just far, far ahead of anything that was happening in the West.
There's one on the end of the same row.
Thank you very much. It was impressive seeing Birūnī's phases of the moon, although that was relatively close, I suppose, in the heavens. But I was intrigued by the point. I just wanted to check I understood it rightly when you said when he interrogated the data of whether he could rationalize something, it was to do with the fact, well, the Earth must be moving, yes, or the cosmos must be moving.
Yes, yes.
Can you speak a little bit more about that? Because I mean, if one didn't solve the problem, did the other?
There was always a sort of secondary tradition about. Which is often associated with Pythagoras, of the Earth moving, and so that's why we just have the impression that the heavens are moving, but it's really the Earth. Once you have the Ptolemaic system established, as it were, and Ptolemy starts his Almagest by proving, as it were, and that the Earth is stationary in the middle of a moving universe. But you still have inklings of this other way of explaining things, especially amongst the Indians. And it is interesting that Birūnī, unlike most astronomers writing at the time and before and after, he is open to the view that the Earth could be moving. You can explain the phenomena just as well with a moving Earth. And then, when he says, but the physicists, it's up to the physicists to prove that it isn't, I think he could say, well, who's right? Is it the physicists or the astronomers? So,
There's another question there. In that row there.
Thank you. I suspect actually a physicist might say on the last question it depends on their frame of reference.
Yes.
However, my question follows on from the question before last, because there was such a centre of scholarship back in the 11th century.
Yes, yes.
And the first part of the question is, how did they lose it? And the second question is, how did all this knowledge in its original form come down to us intact?
Well, many people would say that they didn't lose it. What happened is that you have a continuous development in astronomy through people like Nasiruddin al-Tusi, and Al-Istiji and various other people who were associated with the great observatory in Samarkand, Ulugh Beg in the 14th century. And that's indeed the Copernican revolution occurred because an inkling of these new discoveries amongst Arabic or Islamic astronomers came to the West, probably through a Greek intermediary. So the reason why we say, or why the received opinion, is that Arabic sciences stagnated, as it were, after the 11th century, is that no more Arabic sciences were actually discovered or transmitted to the West. And after the end of the 12th or the early 13th century, you don't have any more translation because of the perception that one knew everything about astronomy and geometry and mathematics in the West. So there was no need to import anything more from the Arabs. But things were still happening in Samarkand, in Maghara, and so on. And it's just that we're not so well aware of these developments.
Right, well, I think we should stop there. We've had 15 minutes of questions, but also it's a perfect place to stop because you're sort of pointing towards the future, which is going to be the subject of the next talk. And I think it's a great testimony to the richness of your talk that you've generated so many very interesting questions on a very wide range of topics. So thank you very much indeed for a fabulous talk.